So, a wonderful good morning, good afternoon, or good evening, depending on wherever you are, and welcome to yet another talk in the Back to Basics track. So the Back to Basics track is supposed to bring comprehensible, easy to understand talks, and this one is no exception, as it is about exceptions. So allow me to, first of all, introduce myself. My name is Klaus. I'm doing C++ trainings for a living since approximately 2016. And apparently this is not even enough C++ for me. I'm also the author of a C++ Smart library called Blaze, and I'm one of the organizers of the Munich C++ user group, which, by the way, since now everything has turned into virtual, may be a pretty interesting point anyway. Munich seems to be one of the most attractive, most active user groups worldwide. And since it's kind of in the middle of a lot of potential countries, a lot of people can join. So please check out the Munich C++ user group. There might be a lot of content interesting for you. However, back to topic. Today we are talking about exceptions. And I want to start with the exception situation, because I believe this is actually one of the most important, most interesting things to talk to about when you talk about exceptions. Then we do a short recap. We talk about how do exceptions work. And then we focus in depth on how to work with exceptions. So best practices of the exceptions handling, and we'll go into a lot of details here. Well, let's get started with the exception situation. And you indeed might wonder, there is recently a lot of talks about exceptions. For instance, right in the time slot after this talk, there is a talk about exceptions. And you might also remember that last year at CppCon 2019, there was a talk about exceptions also. There is probably a reason that exceptions are pretty en vogue nowadays. And it probably all started with a paper from 2018, Zero Overhead Deterministic Exceptions Throwing Values. Herb Sutter proposed this in 2018. This is the fourth revision, therefore 2019. And there's a couple of pretty interesting points that he makes. So I scroll down a little bit and go to a couple of bullet points. Major coding guidelines ban exceptions, including common modern guidelines endorsed by the world's top advocates of C++ exceptions. For example, the Google C++ style guides bans exceptions. The Joint Strike Fighter Air Vehicle C++ coding standards, or short JSF++, was produced by a group that included Björn Strustrup and is published on Strustup's personal webpage and bans exceptions. Many projects ban exceptions. In some survey in 2018, 52% of C++ developers reported that exceptions were banned in part or all of their project code, i.e. most are not allowed to freely use C++'s primary recommended error handling model that is required to use the C++ standard language and library. So as kind of an in-between summary, this is an intolerable rift. Large numbers of C++ projects are not actually using standard C++. And that is indeed the situation. A lot of people cannot use them, do not want to use them for various reasons. And that despite the fact that exceptions are actually rated a pretty decent way to report errors, or to propagate errors. For instance, in 2018, Phil Nash and Simon Brandt compared different ways to deal with errors. And they pretty much compared everything that is available, return codes, but also error flagging, also a couple of things, but also, of course, exceptions. And I rated them based on these 8 categories and found that, after all, exceptions are not totally bad. There is a couple of things where they really shine. However, there is, of course, also a couple of things where exceptions do not shine. One of the most obvious things here is the rating of 1 for overhead in the error path. That definitely is one of the things that people do not like about exceptions. Exceptions incur an extreme performance overhead in the failure case. And to give you an idea how big this performance penalty is, I'm borrowing a slide from Neil Douglas's Introduction to Proposed Expected from Meeting C++ 2017. In his talk, he presents this slide, which I don't want to go into detail. It's not so interesting what exactly is compared here, but there's a couple of things that apparently have low bars, and there is exceptions, these yellow bars. And the most important detail about this slide, I believe, is the left-hand side axis. It is a logarithmic scale. Logarithmic means that exceptions, if they're truly thrown, are orders of magnitude more expensive than anything else. Now, return codes, returning expected things, orders of magnitude more expensive. And of course, this can be a significant problem in many project situations. But this is not it. There's more, unfortunately. There's one point that is always brought up. That is that exceptions make it hard to reason about functions. Does a function throw or does it not throw? And if it does throw, what does it throw? So which kind of exception is thrown? That is indeed something that is a little harder to deal with. There's only one exception that we'll also take a look at a little later. Of course, you can declare a function no except, but that's the one exception. I know it will not throw, but about all the other things, I still have to wonder. Something that also is a deal breaker for many people is that exceptions rely on dynamic memory. That indeed can be a deal breaker, especially in the situations where you're not allowed to use dynamic memory. Exceptions need that because, as a matter of fact, sometimes several exceptions might be required. And all of these exceptions might actually have to allocate something of a dynamic size, something that is not known beforehand. That is, of course, something that potentially makes a big problem. And then last but not least, exceptions make the binary size grow. Both common approaches, the so-called frame-based and the so-called table-based approach, result in an increased binary size. The compiler stores some information somewhere that helps with dispatching the right kind of handling. So it's some kind of dispatch tables. Where is the right catch handler, for instance? They're not for free, and so they have to be stored somewhere. The binary size grows. So in other words, this is not zero overhead. There is something to pay when you use exceptions. However, all of these problems hopefully will go away if indeed there is this major overhaul that is proposed in this paper. I have to tell you that this is not the only approach. By now, there is a couple of papers out there that basically try to figure out what is the right approach. But in other words, there is happening something. Something is on the horizon. And if all of the things work out as anticipated, then potentially, and this is one of the last messages that was given in the already mentioned talk, exceptions could actually become something that is very, very good. Now, almost flawless in terms of these numbers here. So, of course, this is a pretty hot topic nowadays and something that stirs a lot of interest because suddenly on the horizon, exceptions might actually be something that even all those projects that today cannot use them might be able to use. So our ultimate goal is to make exceptions usable for everyone. This is one part of the story. The technical thing, making exceptions useful for everyone technically, this is something that you will hear about a little more in the talk directly after this slot. So in the next time slot, Inba Levi will talk about exceptions under the spotlight. This talk is more about teaching how to work with exceptions properly and implicitly how to just write good code. Because ultimately, this is what exceptions teach us. Good code works pretty well with exceptions. Other code does not. And so perhaps for this talk, I want to actually try something. Perhaps it works out, perhaps it does not. Because it appears that this is a talk for two different kinds of communities. The community that can use exceptions and the other part of the community, almost half-half, that cannot use exceptions. For this talk, I will try to perhaps bring these two communities together. And primarily, I want to focus on how to write good code that can also deal with exceptions well, but of course is also good from a lot of other points of view. All right, so let's do a quick recap on how exceptions actually work. And there's a couple of important things that you should always keep in mind. The first thing is that exceptions usually have to do with 3 keywords, and that is throw, which is here, for instance, try and catch. So in this little example, I have a function f that may have some local variables, and that under some condition throws an exception. This function f is called from some function g that also might have some local state, and which is ultimately called by a main function, which embeds this call and try catch block. So one thing that is pretty obvious is the throw and catch are pretty far away from each other. At some point, you actually find something wrong, report this error, and at some completely different point, potentially pretty far away, you actually deal with this particular problem. Which may be actually a beauty about exceptions. You do not see something in between. In between, it is just as if everything would work out. So here in G, I just call a function, and I just rely on the fact that things are handled. Because if in fact an exception is thrown, then something pretty good happens, something called stack unwinding. Function f has some local state, the string s. And the first thing that happens is that this s is properly destroyed by its own destructor before I go back to the actual call site. The function g also has some local state, the vector v, which is then destroyed next before I again go to the actual call site. So note, objects are destroyed in reverse order of the construction, quite naturally, because this is exactly what needs to happen if I basically jump up or go up the call stack. Then finally, in the try catch block, the exception is caught and handled. However, the stack unwinding is not something that you can take for granted. If you would omit the try catch block, then nothing keeps the exception, nothing catches the exception would leave the main function. In case that happens, the exception is not handled and no stack unwinding occurs. On the contrary, a function called terminate is called, and terminate is a function that is not particularly pleasant. It basically just terminates your process, and as I said, a lot of things do not happen, no stack unwinding, no destructors are called, and so resources are potentially leaked. So it is definitely reasonable to at least catch exceptions somehow, and if you don't want to react to them in any way, a so-called catch-all handler might do the trick. A catch-all handler is just about catching anything. You cannot deal with this very specifically at this point, but at least you guarantee that the stack is properly unwound. So at this time, you might already have a couple of questions. Since there is directly after this talk a subsequent AMA session, I will take all the questions at the end. So if you have a couple of questions, please write them down and do not forget to use the slide numbers. This definitely helps in finding the right slide again. Which brings us to the biggest part in this talk, best practices of exception handling. And the first question that people usually deal with is, when should I use exceptions and when not? Of course, assuming that you're allowed to use exceptions in the first place. So, to summarize, use exceptions for errors that are expected to occur rarely. You've just seen that in the error case, the performance penalty is pretty high. So I would not use exceptions for something that occurs pretty often. Use exceptions for the cases that are truly exceptional, that occur rarely, and probably also in which cases you do not really care about performance anymore. The real problems. Then use them for the exceptional cases that you cannot deal with locally. So for instance, cases like file not found. You have no idea what to do if a specific file is not found. Probably you have to communicate this upwards to a point where you can go to some backup strategy. Or you cannot find a key in a map, although this was something that you were absolutely expecting. Then use exceptions for operators and constructors. Operators, for instance, like operator plus, operator minus, so the things that have a natural return value, and it does not really allow you to return anything else. Constructors, on the other side, cannot return anything. And so this is two examples where it's quite natural to use exceptions. They provide a different exit point from these functions, and so you don't need any kind of return value. Now, of course, if you cannot use exceptions, this is usually a problem. Operators, constructors, they usually pose a problem. There may be solutions to that also. For that case, in case you're interested to deal with constructors in a convenient way, I will refer you to this short lightning talk, fixing two-phase initialization. Two-phase initialization is what is usually done in that case. But if you do it right, you actually can cope with the problem pretty nicely, pretty naturally. However, you should not use exceptions for errors that are expected to occur frequently. So if indeed something it happens very, very often, perhaps there's a better way to report that something happened. That may, for instance, be for functions that are expected to fail. So for instance, a function that is supposed to convert a string into an int. Let's call this function toInt. It gets a string as a parameter. It is kind of expected that the string here cannot be converted. So perhaps this is an example where I simply do not throw an exception to notify the user that something went wrong, but to perhaps return an optional. In the case that something didn't work, the optional is returned as a no-opt. Else, you just return the according number. That's quite natural. Although, of course, an optional does not really express some bad thing happened. For this reason, std_expected was proposed, which is a little closer to the actual thing. Either you get an int or something that represents an error. So it's a little closer, a little more specific, but unfortunately std_expected was not standardized yet, so it's not part of C++20. Perhaps an alternative is to rely on the original, the boost outcome, which is kind of the predecessor of std_expected. So if you write this function like that, it's, I believe, a little easier to comprehend, because it does not, the function does not pretend that all strings can be converted into an int. It's a little easier to deal with this. Then don't use exceptions if you indeed have to guarantee certain response times, even in the error case. In that case, exceptions are truly a bad thing to work with, because unfortunately this response time, it feels a little bit unbounded. Of course, you might measure explicitly and find that it still works, but I would argue there is a certain risk. This is exactly one of the things that needs to be repaired. It's mostly about the implementation of the compilers. And so there can be something done. It just might take a little time. And last but not least, do not use exceptions for things that should never happen, like dereferencing null pointers, out of range access, use after free. This is not exceptions, errors, this is bugs. Bugs that you should fix. This is something that you might simply report when assert, crash right away, and it should be fixed before it goes to the customer. Or of course, you find other ways to deal with this. This is not exceptional cases, this is just plain bugs. All right, again, note down the questions. I will take all of them in the end, so please keep them coming. Let's deal with how to use exceptions properly. And there's a couple of reasonable common advice that you get when you deal with exceptions. The first thing is that you should build on the already existing hierarchy in a standard library, the exception hierarchy. Standard exception is designed as a base class. And this slide is something that you don't have to read, just should give you a feeling of there is already quite a lot of possibilities that you have. So std_exception is in the center, and this is a base class for instance, logic error and runtime error, which on their own are, again, base classes to a lot of much more specific errors. I believe you will find a spot where your special kind of exception fits in quite well, and so you can build on this exception hierarchy. Standard exception is also the one base class in the standard library that you need to know. Everything else is probably something that you will only in rare cases visit, but this is the one base class that is indeed interesting, that you are supposed to inherit from. Then throw by R value, which means you can throw arbitrary things. You can even throw pointers, you can even throw references, but this is not a particularly good idea. The good recent convention is that you throw something directly by value. In this case, I'm doing that. I'm creating a runtime error, which could even be const. I give it some message and I throw it. But why give it a name? There's not a lot of point. Perhaps there are special cases, but in this particular case, the common advice is just to throw the thing directly. Throw std runtime error. So I do not throw something that has a name. I do throw something that does not have a name. That would be an R value. And that, of course, enables the compiler to deal with this a little more efficiently. Although, as we've seen before, the performance of throw might be so bad that you do not really benefit from this particular optimization. But still, it's reasonable advice. And last but not least, catch by reference. You can catch by a lot of things. You can, for instance, also catch by value. To some extent, the catch clause works indeed like functions argument do. In this case, I now catch by value, get something by value. But as if we've seen is that standard exception is a base class. And of course, there is a couple of disadvantages if you catch a base class by value. First, creates an unnecessary copy, which, since it's the base class, might not be too bad, but definitely bad is that it now slices the type of exception. The real thing, whether it's a runtime error or a logic error or something else, is lost. And so therefore, the common advice is to catch by reference. Usually reference to const if you do not want to modify the exception. But if you want to, well, of course, you can also catch by non-const reference, mutate the exception, and then potentially rethrow it again. All right. Which brings us to some extent, the core of the talk, writing good code. And first, we should talk about something that is called the exception safety guarantees. And this already sounds a little bit like good things. The name guarantee suggests that there is some promises that we are making. There is, in fact, 3 different levels of exception safety guarantees. The first level of exception safety guarantee is called basic exception safety guarantee. That already is pretty valuable because, first of all, it promises us that invariants are preserved. As invariants are the one and only thing that you can trust, that the one thing that definitely needs to be something that you can count on, this is already pretty valuable. And second, the basic exception safety guarantee promises that no resources are leaked. Also something that is particularly valuable. What this does not promise, however, is that state does not change. So if you call a function that gives this guarantee, let's assume it's a member function, then the state of the object that you call this function on might actually change. Since it promises that invariants are preserved, it is a valid state, but it is not necessarily the original state. If you also want to promise that the original state is preserved, then we need something called the strong exception safety guarantee. That additionally, so it again promises invariants are preserved and no resources are leaked, but it additionally promises that no state is changing. In a database, we would call this a transaction. And we also refer to this as commit rollback semantics. That, of course, is absolutely great because this is something that really feels easy to use. So I call this function, either it works or nothing has changed. Really beautiful, but unfortunately, it's not always possible. So for instance, imagine that I'm reading something from a socket, this fails. I might not be able to read it again. Same is true for streams. And it might not always be reasonable performance-wise. This is something that we'll see again a little later. Sometimes it could be done, but we just don't want to pay the cost for it. And there is even one more guarantee, an even stronger exception safety guarantee, and that one is called a no-throw. or sometimes also known as fail guarantee. That guarantee simply says the operation cannot fail. It will not throw an exception. And this is nowadays explicitly expressed in code with no except, which I'll talk about a little later. So this is the 3 exception safety guarantees. And this is now what we want to apply in code directly. We want to see how code works with these particular exception safety guarantees. So let's consider an example. And as I said, this is not just about exceptions now. I want to really make the point that this is about writing good code. Code that you can reason about, code that works reliably, and that you just have a good feeling about. So whether or not you're using exceptions is indeed irrelevant. You want to write this kind of code. And interestingly, exception safety is just an outcome of writing this kind of code. So to some extent, I'm now building on a talk from John Culp from CppCon 2014, I believe it was. The talk was also called Exception Safe Code. And in this talk, he starts by making a promise. Actually, it's 3 parts, and this promise holds for all 3 parts. The promise is that if you follow the advice, the code is easier to read, which implies it is easier to understand and maintain. And I now add that it is even more correct with a much, much higher probability than if it would not be. The code becomes easier to write as well, which is of course also great. There is no additional time penalty, and it should be 100% robust. You should be able to just trust the code, look at the code, and know it is working correctly. All right. The example that I have is widget class. And this class, first of all, comes with 3 data members. It comes with an integer, which I by default initialize to 0. It comes with a string s that by default I initialize to an empty string. And it comes with a pointer to some resource, a raw pointer initialized to null pointer. I should already at this point point out that PR may be null. This is part of the semantics of this widget. So if this is null, the invariant might still be preserved. That's okay. One of the things I definitely want to do with a widget is that I want to copy it. And so first of all, I write a copy constructor, which is pretty straightforward. So given I have some other widget, I first of all copy the integer, I copy the string, and then, well, I copy the resource. And I do not copy just the pointer, which would be bad because copying a raw pointer here would probably cause some trouble later in the destructor. No, I'm really copying the resource as such. So I'm creating a new resource, literally, and assign this to the pointer PR. Of course, I'm only doing that if the given pointer, so the pointer inside this W here, is not a null pointer. Else I just stick to the null pointer that I also have. So that's a copy constructor. We can take a look at this, and we feel pretty confident that everything we're doing in this function is just okay. Very straightforward. Deal with the int, deal with the string, deal with the pointer. Then, however, I also, for symmetry reasons alone, want to copy assignment operator. That, as you see here with these braces, is apparently a slightly longer story. So I start with something that I used to forget pretty often, and so it's nowadays the first thing I write, the return statement. Now the canonical return asterisk list, that's the first thing we do. However, from a logic point of view, the first thing that we do is, of course, we copy the integer. Well, okay. Then we copy the string, also pretty straightforward. And we copy the pointer in the sense that we create a new resource that deals with this copy operation. So copy constructor of resource. Okay, you already see that something's missing. I am missing the check, of course. I also, again, have to deal with null pointers. w.pr could be null. I should check for this first, and then it actually works well. However, something still does not feel quite right. Oh yes, of course. What if the given pointer is null? And what about the fact that actually I'm assigning to a pointer that might already have been holding a resource? Oh, there's multiple things that we should take care of. So first of all, I definitely should take care of my old resource first. I do not want to leak any kind of memory, so I delete the pointer. And then, of course, I said potentially the pointer is null, so I need an else branch too. An else branch that probably sets PR to null in case the other pointer is null. So I want this widget to be a real copy of the other widget. Whew. Okay, this was already a lot of work, a lot of details, but something's still missing. And yes, you might already see that a special case is missing, an edge case, self-assignment. If indeed, accidentally or because it's just a semantical thing, this W here is the same as this widget, then actually this is not really working well. Now, this might work well, perhaps this does, but I'm definitely destroying my old resource and then it's gone. And this definitely is not what a user would expect if it assigns a widget to itself. So I should protect myself against this by means of a canonical self-assignment protection statement. Okay, now it feels a little bit like we can lean back and be very proud about ourselves that this is actually now working well. You may anticipate, however, that this is not the end of the story, because this line here gives us a lot of trouble, potentially. New could fail. New could actually throw an exception because it does not, is not able to give you enough memory. If indeed you don't have enough memory, you probably have totally different problems. This may be the one thing that you cannot really cope with. But also the constructor of resource might throw an exception. And if that happens, we are unfortunately in a pretty bad state because we have already deleted our old resource. And the delete operation frees the memory. This is great. But it does not reset the pointer. So if indeed the constructor of resource throws an exception, I have a dangling pointer. And so the invariant of my class is completely destroyed. You would expect that in the destructor, I simply delete this pointer too. Now imagine that in the destructor, I now find a dangling pointer. I would try to delete the resource a second time. Of course, this doesn't work. And perhaps this is more like a silent error if your standard library is not configured accordingly, but perhaps it also crashes. And if you see the crash, it is miles away from the line where actually the problem occurred. And so this is really, really bad. Broken invariant is probably the worst thing that can happen to you. Perhaps I can visualize this even more by telling you that this is perhaps a toy example. Consider some real example, some ATM machine. Consider that somebody has written a class bank account, and this bank account comes with a withdraw money function. Well, you pass some amount, and the first thing you do is to reduce the balance by this given amount. Okay. Now, the next thing is that we have to do is we have to prepare the cash that the user of the ATM machine then finally gets. What if prepare cash does not really work, throws an exception? Well, then of course I have a significant problem either, because the balance has already been reduced. What is the obvious solution in this case? Well, of course, it is a try catch block. Try, prepare cache, and in case there's something happening, any exception is thrown, then of course we increase the balance again. Is this really the kind of code that you want to happen behind the covers in an ATM machine? Is this the way you want your money to be treated? Let's admit it, this is just bad code. Code that is not really reliable. Yeah, what if increased balance throws another exception? The money is gone. It might be entirely gone. And a lot of people believe that the financial crisis was responsible for the bankruptcy of the Lehman Brothers. I believe it was because of invalid objects. Invalidated invariance. And if I am to predict the future a little bit, I might not be good at that, but if I would predict the future, then probably broken invariants are also a reason for the fall of mankind. And if I go to a further future, or farther away future, then probably broken invariants are also the reason for the rise of the empire. I'm almost certain about that, because in 2014, we already got the right message. So both John Culp and his friend Yoda tried us to tell that there is no try. Good code is easy to understand and is not about fiddling with all the details. And this is exactly what is happening in this function. Despite the fact that this assignment operator is only about 10 functions long, it is just too difficult to really comprehend. We're dealing with virtually everything. We are dealing with memory management. There's a new, there's a delete. We're dealing with pointers. Yeah, so there is dangling pointers involved. There's null pointers involved. We are dealing with all different kinds of data members. Yeah, all of them in a row. We're dealing with self-assignment. It's just too much. There is, however, very, very good advice on how to deal with this kind of thing. Delegate. So first of all, this function is what we say is exception unsafe. So right now, this code gives us no guarantees whatsoever with respect to invariance and resources. There is a simple fix now. A simple fix would be to move the else branch, so this line of code here, to line 25. In case we do that, actually we have saved the day. Because if either new or the constructor of resource fail, we're still in a good shape. I said that it is perfectly okay if the resource pointer is a null pointer. So this is potentially okay, but it might not be the old state, because I've already changed in line 22 the integer and in line 23 the string. Still, this is what we refer to as the basic exception safety guarantee. Essentially means we are in good shape. Yes, there was a problem, there was an exception, but still we can deal with the problem. We are still in good shape. We have somehow dealt with the problem locally. No resources leaked, invariants are preserved. But I would still rate this as bad code, because still it is just too many details that I'm trying to deal with manually. So as I said before, the right solution is to delegate. Instead of dealing with all of this memory management manually, what I should do really is to use a unique pointer in this example. So I have a unique pointer here as a data member now. I use make unique in the constructor, and I'm also using make unique here in this line. And suddenly, a lot of the complexity that we've seen before is simply gone. We do no longer have to delete. We do no longer have to call new manually. It's all handled automatically, reliably. True, we did not go beyond the basic exception safety guarantee yet, but still, it feels and it looks better. We take a look at this code now and we have a much better understanding what is happening. What I'm using here is just the basic philosophy of the C++ programming language. What I'm using here is RAI. Resource acquisition is initialization. And I will not talk a lot about RAI at this point, because also here there has been a very good back to basics talk last year at CppCon 2019. So Arthur O'Dwyer talked about RAI and the rule of zero. And this is a talk that definitely every C++ programmer should have seen, or every C++ programmer at least should have understood the full extension, the full extent of what RAI truly means. There is no resource leaks in C++ if you truly follow this guideline. Or, to put it into John Culp's words, keep your resources on a short leash to not go leaking wherever they want. Now, indeed, Rai is helping you a lot with resources, but that makes your code much easier, to some extent automatically exception saved. So it will not always work. Still, this is a very first step to go there. Still, we can now, although we are pretty happy already, perhaps, we can still try to reason about this one more time. Because still, whatever happens in make unique might fail. We still call new inside this function. We still call the constructor of resource. It might throw an exception. However, perhaps we can take a closer look at what we're doing in this function. We're copying the int, we're copying the string, we are copying a resource. Isn't this something that I'm also dealing with in the copy constructor? Isn't this exactly the same piece of code? Actually, it is. And for that reason, we can actually go one step further and apply something that most strongly follows the advice that I've given you before. Delegate. Instead of coding this again, to some extent violate the try principle, we could simply call the copy constructor. So now in this function, we have dealt with all of these operations. If indeed this line here, line 14 fails, nothing bad happened. Actually, it just failed to create a copy, which is nice. So this line is the one line that might actually fail. If I now can make the content of temp my own without any possibility of this operation to fail, then I actually would be done. And there's a very elegant way to do that. The most common one used today is to simply move this temporary into this. In other words, to use the move assignment operator. That is called the temporary move idiom. And it works, hopefully, because your move assignment operator, if everything is implemented as expected, should actually be a no except operation. An operation that promises that it will not fail. So if I experience an exception in this line of code, then actually nothing bad happened to this subject. I did not yet touch this state. This is great. This is what we refer to as the strong exception safety guarantee. Either everything works out or nothing is changed. Invariants are preserved, no resources leaked. Perfect. But if this works, if I indeed get a full copy of W, if I get this temporary, then I can move it without any possibility for any kind of exception into myself. The temporary move idiom. And suddenly, a lot of the complexity is indeed gone. If you take a look at this function, we now simply argue this works. And of course, the move assignment operator implements something that we call is that this no-throw exception safety guarantee. This operation will not fail. We heavily rely on that for implementing the strong exception safety guarantee. There is, in fact, a couple more functions that are not supposed to fail. So move just being one of them. The most prominent function that must not fail, should not fail, to weaken it a little bit, is destructors. Destructors are an integral part of this entire game because they are called during stack unwinding. If a destructor could fail, if it could throw an exception during stack unwinding, when another exception is obviously already flying, then we would again fail completely. If you throw a second exception, meaning if indeed two or more exceptions are flying, then the standard terminate function is called again. And I said before, this is a not particularly pleasant thing to happen. This is something you want to avoid. Because they're so important in terms of program correctness and exception safety in particular, destructors are implicitly marked as no except in C++11. So you can, of course, mark them yourself, but the compiler assumes that there are no except. If indeed you want the destructor to throw, then what you would have to do is to explicitly mark this as no except false. So cleanup must be safe. The second function I already mentioned, the move assignment operator, but of course there's also the move constructor. Move operations in general should be implemented such that they can promise not to fail by means of no except. So there is even a core guideline C66 that says make move operations no except. There's very, very good reasons because usually the move operations should really be broken down into the most simple operations. Copying pointers, copying integers, it should be simple. And even though it may be a little more expensive, every move operation can be made no except. Of course, it is your choice in special cases. And the third function that should always be no except, because it usually can be implemented in that way, is the swap function. Also, swap usually should be able to be implemented in terms of non-failing basic operations, like copying pointers, like copying integers, etc. Standard swap relies on the move operations, and if the move operations do not do what you expect, what you want, of course you can implement your own swap. In that case, please remember that swap indeed should be no except. No except has indeed a couple of benefits, so it is something that perhaps you want to look out. No except, first of all, makes the promise to never throw visible in the code. So you will definitely see in the code that something will not fail, and this is a good thing. This definitely raises your confidence in this particular function. But it also can lead to, well, at least slightly faster code. It's not massively faster, but it has been shown that indeed the compiler has to produce a couple of less assembly statements. And of course, this may make a difference between a little faster and a little slower. Note that if you indeed mark a function with no except, and you still throw from this function, so an exception leaves this function, then again terminate is called. And unfortunately, the compiler does not really check this, this promise that you do not accept. This is something that compiler has never done before. Before C++11, the compiler did not check any kind of exceptions. You're on your own here. So if you give the no except promise, then make sure that it is true. And make sure that you can also give this promise. The compiler will not help you. Which, however, also means that you should not give the no except promise lightly. So only give it if you're absolutely certain that this is actually true. And also, do not give it if you later potentially might take it back. Because once a function is marked as no except, people will rely on this promise. And later telling them, by the way, it's not working that way anymore, is probably not a good idea. So there is few functions that should be marked with no except. The obvious small functions, please don't overuse it, despite the fact that perhaps code is a little faster. So, and of course, I mentioned this before, destructors are implicitly marked as no except. So back to this example. By means of this construct, we have now turned the function into something that we understand immediately. We can take a look at the function, we see it works. And I would argue this is just good code. Code that is comprehensible, code that the reader can pick up easily. And so even if exceptions are not your thing, this is still something that is interesting from a structural point of view. This code is just properly structured. And so if you implement your code in this particular fashion, then you might in the future, when you can turn on exceptions, you might actually have a big benefit. Note that when this is working, we can actually also completely get rid of this statement here. Self-assignment will still work. It might be a little more expensive, but still it works. And so this is exactly what John Culp meant with his promise. The code becomes easier to read, easier to write. There's nothing special that we're doing. We've done the same thing before, and it is 100% robust. So, a couple of guidelines. RAI is the single most important idiom of the C++ programming language. Use it. All functions should at least provide the basic exception safety guarantee, if possible, and reasonable, the strong guarantee. And consider another guarantee, but only provided if you can guarantee it even for possible future changes. All right. Now there is a perhaps interesting side question, how to deal with failing cleanup functions. What if, for instance, a destructor calls something that could potentially fail? So, for instance, let's assume that we have a file that has been opened somewhere in the constructor probably, but now that has to be closed in the destructor. Well, fclose actually can fail. It's not that obvious, but it will return an error code. What if I want to deal with this problem somehow? Well, then the best advice I can give you is that you do not rely on std fstream or so ifstream or offstream, because in this case, they simply ignore the problem. If you want to react on this particular problem, then you would have to write your own RAI class. In the destructor, you would now accept this error code, check it, and deal with it somehow, but you still cannot throw. You should not throw. You now know what you could do, but still it's not a particularly good idea. It will trigger too many other problems. So, for handling errors in the destructor differently, write your own RAI classes that manage this in the way you want to deal with it. Now, there is perhaps one more information that I want to give you, something that is always something that I also deal with in my training classes, how to refactor code that just isn't there yet. How can I get to code that is exception safe, that is beautiful to use? What do you have to do? Well, basically, we are now talking about the transition from pre-exception safe to exception safe code. So this is, we're dealing with code that cannot really deal with exceptions at this point. And there is one law, one rule, I would say, not just as strong from a wording point of view. There is Jean Perrin's iron law of legacy refactoring. Existing contracts cannot be broken. So what does this mean? Of course, you should refactor, but you should not make the old functions suddenly throw exceptions. All new code that you write can be exception safe, can be written in the way that I basically now just talked about. All new interfaces, of course, free to throw as well. Yeah. However, if you have some old function, you cannot just leave exception, let this old function throw exceptions now. Nobody would expect it. And it would, of course, very ungracefully disrupt a lot of things. So you have to basically write new functions and re-implement the old function in terms of the new one. So in order to give you an idea how this works, let's take a look at an example. It's not a particularly difficult example. It's a rather short example, something that gives you an idea what I have in mind here. It's a function that loads a file. So I'm loading a file. I have in this class some member that tells me from which file, and everything that I load is written into this byte stream. This implementation now uses error codes. And I should say this is actually a nice way to use error codes. It's still easy to understand. It deals with everything properly. This is okay. So I first of all open the file with some things. So the details are not so important. I open it, and if this fails, well, no problem. I return that there was an error. If this was okay, though, I first query the size, which might fail. If this, however, failed, I simply close the file and went on. And if this works, I really do the reading. As I said, it's more about the structure now. It's not about the details. Now, you can refactor this very, very elegantly. You just have to also, first of all, rework file. Because file, as long as it works with error codes, will not really work. So let's assume that file has been restructured following these right principles. Now the constructor opens the file or throws an exception. Of course, the destructor calls Klaus when necessary. Get size and read. These two functions also throw an on error and return whatever is expected. If you do that, then the function suddenly might look like this. You open the file. If this doesn't work, nothing bad happens. But if it works, I can continue to deal with a byte stream. The byte stream constructor might fail, but then file is cleaned up. Everything's okay again. And if this works, I can read, and so on. I do not have to explicitly deal with errors anymore. Note that this function is now called differently. It has also different semantics. It gets a file name as a parameter. It returns a byte stream. I changed a lot. But this might be the function that I need. And that here is the old function. The old function that I called before, this function is now implemented in terms of the new one. I embed the new function in a try-catch block and simply return what I returned before, true in the case of success, false in the case of an error. It is the same code, but suddenly it's so much nicer to read, so much nicer to deal with. All right. And so, yes, you can indeed deal with this, with these steps, even in a large code base, because usually you deal with this in small bytes. It should be part of regular maintenance, and the big code base is never at risk. You can actually deal with this locally. So, and again, I point out this is exactly what John Culp meant with his promise. Code just becomes more beautiful, more readable. So, I hope that this was reasonable, gave you a reasonable idea of how to work with exceptions, but also that a lot of the problems that we have with exceptions are not really about exceptions, but about the code that is surrounding the exceptions. Writing better code, dealing with exceptions actually becomes easier. So thank you very much for your attention. And of course, I'm happy to take a couple of questions if there's time left. All right, so there is a question. Can you re-explain potentially slices the exception under the topic of catching exceptions by reference? So potentially slices. Let me see if I can really quickly go back to this slide. That might make it a little easier. So here we are. So potentially slices. If you throw an exception object itself, it's not sliced. But as soon as you have anything that is deriving from exception, it will definitely be sliced. So it entirely depends on what you actually throw and what you expect. In case you catch standard exception, I would guess that this really causes slicing. But if you throw something different and you expect it in exactly that form, it is just copied unnecessarily. It is not necessarily sliced. It entirely depends on this combination. Okay, second question. In an embedded system that is multi-process and multi-threaded, is it workable to allow exceptions in any process without real-time deadlines and restrict in process with real-time deadlines? Okay, this is definitely a great question, a longer answer. However, this is perfect for the subsequent AMA section. Yeah, so I coolly invite you to just post the question again. Probably I don't have enough time to answer this in detail now. Which means I'm going to slide 78. Let me quickly go there. For the third question, how does the use of make unique handle disallocating the memory and then allocating again in the copy constructor and copy assignment operator? So make unique is essentially just calling new. It is a wrapper around new, which is fairly convenient because indeed in this code you never have to deal with new or delete yourself. In case, however, anything happens during this new and the subsequent constructor, there's never an object that is created. Make unique fails, completely, and there's never any result. It never returns me something that has been created because nothing has been created. And so it's not really a problem for me. There is no responsibility that I need to take care of. And so there is no problem with disallocating anything. Perhaps there is one more detail to the story. If new indeed allocates and then the constructor of resource fails, then the new promises us to also deallocate again. So I never get a pointer. I would not be in a position to free this resource because I did not really get the pointer. Nothing was assigned to PR. So I wouldn't have a chance anyway. New takes care of this. It rolls back the memory allocation on its own. So there is a difference between the new expression and operator new. This is something that is important here. All right. I think that's the end of the question. Please, of this session, please, if you have a couple of questions that you really want to be answered, please just stay in this room. There is a subsequent AMA session. You're cordially invited to participate there. Else, thanks a lot for attending. I hope this was useful for you. Thank you very much. All right, so I assume that we are now in the AMA session and that there is now a lot of potential to ask additional questions, not just about this talk. I should mention, I also gave 2 talks on Monday, one about the solid principles, one about calling functions. Perhaps there's a couple of questions that you want to ask. There's also the potential to ask questions about the Blaze library, if you have an interest here. So this is indeed an Ask Me Anything session, anything about C++. All right, so Rich van Leher asked the question, in an embedded system that is multi-process and multi-threaded, is it workable to allow exceptions in any process without real-time deadlines and restrict in process with real-time deadlines? This is exactly the difficult thing about exceptions. The situations could be really, really complicated. This is why, indeed, the time of exceptions is kind of open-bounded. The exception algorithm has to deal with a lot of potential issues. So it has to deal with all kinds of possible inheritance hierarchies, even virtual inheritance. It has to deal with a lot of potential catch clauses. It has to find the right one. And so unfortunately, the time is unbounded, potentially. So as soon as you say real time, I would argue there is currently a problem. Possible? Well, yes. Of course, you can benchmark on a particular platform with a particular compiler. I would argue a target compiler on a target platform. You can benchmark the worst case that an exception takes, the worst time. The hard thing about this, however, is to benchmark this realistically, in a scenario that will exactly in this way also occur in your final program. So you can only benchmark with the real program usually. Benchmark, find what is the upper bound, and you have to do a lot of measurements here because, of course, there may be a lot of variations. Find the worst case and decide whether or not this is something that is working for you or not. This is currently the advice that you can give about exceptions. And whether this is multi-process or multi-threaded or both, as soon as real time is involved, exceptions have a problem with the current implementation. So I hope this, to some extent, answers the question. Else, you have the opportunity to perhaps ask again. All right. Paul asks, how can we know if a third-party or standard library function can fail? There is a simple answer to that question, everything that does not explicitly promise to not fail. So everything that is not no except can fail. So if you see a function that is no except, rest assured it will not fail, because else the terminate function would be called, and that would be a much, much bigger problem, of course. But if it doesn't promise you anything, consider it a throwing function, which sounds a little scary, I admit. But as soon as you embrace the idea that destructors take care of resources, destructors make sure that invariants are preserved, it's not so scary anymore. Indeed, the function still is pretty simple to write, pretty simple, at least convenient to read, and it should still work pretty well. So yeah, consider every function failing. That does not promise that it doesn't fail. Can you give some tips on how to ensure a no-except function will not throw an exception? I have to admit this is a difficult one, because even the compiler struggles here. My personal advice is not to overuse no-except, because indeed there is no easy way of doing it. I could now show you a little example that I also show in my training sessions. If you write a function, make it no-except, and throw exactly from this function, that a compiler, both GCC and Clang, will tell you, wait a second, there's something very, very awkward going on here. You promise it's no-except, but still it's throwing. However, as soon as you embed this throw in another function, they might not warn you anymore. So unfortunately, compilers do not help here. And in big programs, in big libraries, frameworks, whatever you have, big projects, there is no way that you could tell manually if it is no-except or not. Or if a no-except function it has called something that's failing or not. Therefore, use no-except sparingly. Only if you're absolutely certain that it will not throw, and also that after refactoring potential future changes, it will still never ever throw. That's the only advice that I can give here. Okay, so follow up. Exceptions in one process can have adverse timing effects on another process. I admit this is something I never tried. I would argue at this point, unlikely, but a lot of complexity can happen. So I admit this is something I indeed never tried, and therefore cannot reliably give you an answer here. So I use different processes, I use exceptions, but I never really cared about timing issues from one process or another. I never examined it, so I would be the wrong person to give you any advice here, unfortunately. All right. Would you elaborate on how dynamic memory is allocated for thrown exceptions? The compiler internally has to, so when you throw an exception, this exception has to go somewhere. Well, where does it go? The compiler, for that reason, allocates a little memory for itself. It's not a lot, but it has to at least reserve so much memory that a couple of exceptions could fit in there. And because, of course, there is no telling what exception you're throwing, different sizes, well, it's dynamic memory. It cannot predict that it will be exactly that type. So it reserves a little memory up front that it can use in the case of an exception in order to deal with this, with a case, for instance, that all the memory is depleted. Yeah? So if you get a bad alloc exception, still this exception went somewhere, and that is in this pre-allocated piece of memory. How exactly it is handled is, of course, something that compiler vendors can do as they seem fit. I would even argue, it's more a rumor that I know of, that some compilers might have a solution with static memory, but I heard that this is not the most reliable way of doing things. So, okay, perhaps I hope this answers the question a little bit. Okay, next question. What are some cases when we cannot provide a no-except guarantee on constructors or assignment operators? You cannot give a no-except guarantee if inside the function you're calling other functions where you do not know whether they throw or not. In other words, functions that do not have the no-except specification. Because, as I've said before, you should assume that these functions do fail, can fail. So if inside the constructor or any assignment operator or any other function, you call something that is not marked no except, you also cannot give the no except guarantee, which, formulated differently, you can only give the no except guarantee if everything that you do inside the function is no except. Copying integers, copying pointers also, calling swap functions, moving things. That is usually the things that are no except. And of course, if you use something from a standard library or any other library, check out the documentation. For instance, the move operations of a standard string are explicitly marked no except. This is something that I can rely on. Okay. The solid principles. Regarding solid principles, do you recommend using abstract classes widely to facilitate dependency injection and testability? I do not recommend that. Unfortunately, another talk of mine wasn't accepted. This would have answered this question very, very directly. In the community, we have the tendency to remove inheritance hierarchies and also pointers as much as possible. I should not exaggerate. It's not about getting rid of all inheritance hierarchies, but we have realized that too much inheritance is hurtful, which admittedly is not something that we realized only a couple of years ago. This is something that we realized in the 90s already. Too much inheritance is indeed a problem. So I would not argue that using a lot of inheritance just for dependency injection is the right thing. What I would recommend instead is to rely on values. So for instance, instead of passing some function pointer, which is the command pattern, I would recommend to use a standard function object. This is also dependency injection, but this is not a pointer. This is not an inheritance hierarchy. It is based on type erasure. This gives you an enormous additional flexibility. It gives you a lot of certainty that there's no lifetime issues because the thing will be copied. There's no null pointers to deal with, no dangling pointers. It just makes your life easier. So it's not about using inheritance. All of these solid principles are not about using inheritance. It is about the structure of a structure in code. Yeah? And in particular, this dependency injection that you mentioned, or perhaps also related to things like interface segregation and dependency inversion, I would use more modern C++ techniques. Check out type erasure. There's also been a Back to Basics talk last year, also given by Arthur Dwyer. That is the modern way to approach this problem. Dogs or cats? I'm more a dog person. I admit I was tempted to, in my function calling functions talk, to use dogs because a couple of years ago, Stefan Tilave used cats in his explanations, and so I was tempted to use some kind of counterpart, but I did not. So it's neutral. No cats, no dogs, but I'm more of a dog person. All right. When writing a lot of related free functions, how do you like to organize them? In a namespace, struct, util file, etc. I definitely would not put them in a struct because then it wouldn't be free functions anymore. I, however, always tend to put them in a namespace. I never put anything in a global namespace. This doesn't feel right. There needs to be some structure also to free functions. There needs to be something where they belong to. And namespaces are just the right thing for that. I would argue a class is a data container primarily. And of course, it has functions that help you to deal with this data. And namespaces are function containers primarily. Of course, they also contain classes because things should go together. But namespaces are a great thing for free functions. It depends on whether it should go in the same namespace as an encoding class or in a different namespace. This entirely depends on what you want to do with it. So there is no general answer, but usually this is the right thing. And from a file point of view, I tend to first, as long as I don't know anything more, I tend to put it to the class that it works with. And later, when I realize that I can generalize the idea of this function, make it more generic, then I definitely move it into its separate file. This is what I call a shim, for instance, in the Blaze library. A shim is a generic, simple, free function that provides some interface, and that can be overloaded for specific other types in order to trigger similar behavior. Okay, can you explain a little more what exactly is called stack unwinding? So stack unwinding is one of the most interesting things that you have as a guarantee. If you have in a function local variables and you leave the function, and local variables may be a string, maybe a vector, maybe anything that you put on the stack, something with automatic storage duration, then if you leave the function, these things are guaranteed to be destroyed. Any object that whose constructor has been completed, so in other words, every object that has been initialized and that is on the stack will be destroyed with its own destructor at the point where you leave the scope where this object has been created in. That is an amazing thing. This is why a lot of people refer to as the destructor being the most powerful feature of C++, because you can use the destructors due to stack unwinding to clean up things, to make sure some functions are called, whatever is necessary. Stack unwinding merely means that whatever you put on the stack in a certain scope is destroyed at the end of the scope, reliably, with 100% language guarantee. And this 100% is the essence of this, these four letters, this RAI idea. Should complex no-except functions usually have a try-catch? So any no-except function, any function that promises not to throw, must have a catch inside if it calls things that could potentially throw, because no exception must leave a no-except function. So a complex no-except function definitely must do something inside in order to deal with possible failure. Yeah, so try at the beginning, catch at the end, and if indeed you catch an exception, you have to deal with this locally and return an error code or something similar in order to signal that something went wrong. But you must not throw an exception, because else your process simply crashes and the terminate function is called. Terminate, by the way, can be, this may be a little more than back to basic, but it can be customized. You can do a lot of different things in the terminate function yourself. So you decide what's happening here. The default is to call abort. And abort is the function that sends a kill signal and crashes the process. Okay, if an allocation like the one in widget in application code is considered exceptional, can the burden of exception safety be ignored? Okay, can the burden be ignored? I'm not exactly sure what you have in mind here. So can I simply say, well, it fails, I throw the exception? Well, yes, if the surrounding code is structured accordingly. So in other words, if you have things to write and proper structuring, written in code such that all the invariants are preserved, no recess are leaked. That's the key. Else you unfortunately cannot ignore it. You have to deal with it somehow. You have to make sure that your invariants are taken care of. And of course, invariants can be arbitrarily complex. It depends on your particular implementation. In my example, in this widget, I've chosen that the invariant is also okay, so it's not violated if the pointer is set to null. If your pointer must never be null, then of course it's a little trickier, a little harder to do this properly. Okay, this is not just about exceptions, but a general question. I have had a couple of years of career break due to family circumstances. Try to bridge the gap now. Any suggestions for good books? Oh, there is definitely a lot of books. you see in the back, I don't collect books like other people do, but I read a lot of books. And there's a couple that I definitely can recommend. If you really want to catch up to what modern C++ looks like, I would recommend A Tour of C++ by Björn Strustrup. Get the second edition, which is updated to C++ 17. This is the shortest, most compressed intro to C++ that you can get. It's 256 pages, approximately, and there is nothing more compressed than that. Everything else is just more long-winded. Really good from that point of view. There's a couple of classics that I always recommend. There is, of course, the Effective C++ books. I love the first one, Effective C++. I love the newest one, Effective Modern C++. I usually also recommend a couple of books outside of C++ in order to get more ideas about the surroundings. For instance, I also like to recommend The Pragmatic Programmer. That's one of my favorites. It's not a C++ book, but it really gets you into the habit of writing good code. And I think this is a classic. And very similar in this regard is Clean Code from Robert Martin. So 4 recommendations. No, you don't see my email anymore. But if you couldn't write this down now, I would recommend to just write me an email. I send you the references. All right. Now we need the slides again. If you could make the slides visible again, because we need slide 28. There was a slide 28 question. And eventually we have actually to finish, unfortunately, because there is another talk in just a couple of minutes. So how do exceptions work? The question is, I did not send a comment regarding the unwinding when there is no try catch. So actually 27. If an exception leaves main, so if it is not at least caught in main, if the exception is not handled anywhere, then the compiler is actually not does not necessarily have to do anything. Meaning, it can terminate the program at this point, which I said before is usually a call to abort, and kill the process. Which means there is no stack unwinding happening. Yeah, you just crash your program at this point. The string is not cleaned up, vector is not cleaned up, anything in between. As long as it's memory resources, you probably are not particularly unhappy. But if you think more about other resources like files, sockets, and things that you really might want to put back and clean up properly, that is a problem. So resources is more than just memory. There's indeed a lot more that can happen. So the advice was just to deal with exceptions somehow. If you have exceptions enabled, the main function should probably at least, this was slide 28, try to catch anything, just to be sure that stack unwinding truly occurs. So I hope this answers the question. All right. Okay, one more question. Perhaps this is the last one. Regarding solid and inheritance, what is the Back to Basics talk by Arthur O'Dwyer? CppCon 2019. Okay, I think you're referring to his Rye talk, Rye and the Rule of Zero. Arthur did not talk about solid, and Arthur did not talk about inheritance. You might also talk about the type erasure talk. So Back to Basics, type erasure. Perhaps this is what you're referring to. I'm not quite certain at this point. This is the 2 talks I mentioned. All right. So unfortunately, there's still a couple of questions. This is unfortunate, but feel free to approach me at the rest of the conference. Also, feel free to write me emails. To some extent, this is my job, answering C++ questions. And definitely also the last option is to contact me via LinkedIn. I'm easy to find. My name is pretty unique. Contact me there and ask the questions again. So thank you very much for attending. I hope I could help a little bit, clarify a couple of more details. And we see each other at the rest of the conference.